Hi, Jiayi. So for today's interview, you are given a question about the singular value decomposition, or simply put, SVD. So here you have a symmetric 2 plus 2 matrix, which is called A, with two eigenvalues, which are 3 and -2, and they corresponds to two eigenvectors v1 and v2, and the eigenvectors are unique. And the problem is to find the singular value decomposition of A. If this problem is too difficult, you can start by telling me the definition of singular value decomposition of a symmetric matrix.
Okay, thanks for the question. So as you said, let me start with the definition of single value decomposition. So for a single value decomposition, A expresses this form where U is an orthogonal matrix, and in this case, A is 2 plus 2. A is 2 times 2, so U is a 2 times 2 orthogonal matrix, and sigma is a 2 times 2 diagonal matrix. And V is also a 2 times 2 orthogonal matrix. And firstly, I want to calculate the matrix sigma, and we know that the diagonal elements are just the singular values of A. And to calculate the singular values of A, we need to calculate the eigenvalues of A times A transpose. And in this question, it's a little bit tricky because A is a symmetric matrix, so this is equals to A squared, because A transpose is equals to A. And so to get the eigenvalues of this matrix is much more easier, because we know that the eigenvalues of A is 3 and minus 2 and -2, and it's well known that so it's very easy and very obvious to get that the eigenvalues of A squared is just 9 and 4. And so by the definition of singular value of the A is just the square root of the eigenvalues of A transpose. So sigma is equals to this diagonal matrix. And then how to work out U and V, because A is symmetric, there is a more tricky way to do that. So first we can just diagonalize A, because we already know these eigenvalues and eigenvectors. So A is equals to times U1, U2 times U1 transpose U2 transpose, and that is the diagonalization of A, because this is the eigenvalues, and 3 and -2 is the eigenvalues.
Eigenvalues.
This is the eigenvalues. So now we just need to turn this matrix into sigma. So we just need to do a little bit modification to this. So we just turn this negative positive, and we just move the negative to the matrix U. I'm sorry.
Yeah, the negative sign.
Yes.
Yeah. Yes.
Is negative U2. This part is equals to this part, which is obvious. And because U1 and U2 are the result of this symmetric matrix A. So this is orthogonal. This is also orthogonal, which is aligns with the definition of single value decomposition. So this is the single value decomposition that we want.
Yeah, okay, you can stop here. And I think your result is correct and your logic is very clear, especially this part where you derive singular values of A. So that's all for today's interview. Thank you.
Thank you for your comments. Thank you.